back at AP Review. We're doing 2017 BC free response number 5. Let f be the function defined by f of x equals 3 over the quantity 2x squared minus 7x plus 5. Part A, find the slope of the line tangent to the graph at x equals 3, right? So part A, this is a non-calculator problem, right? We need to find f prime. Now, if I were you, you don't have to do this, but I would probably treat it as this whole quantity to the negative first and do a chain rule. You can do it as a quotient rule. There's nothing wrong with it. It's fine. Your numerator, if you chose to do a quotient rule, sorry, wrong way. If you chose to do a quotient rule, it's fine, and your numerator is 3, so d low is going to be a 0 anyway. I'm just going to do it as a chain rule, right? So when I go to find my f prime, right, so f prime of x is going to be negative 3, this whole quantity to the negative second times the derivative of the inside, which is going to be a 4x minus 7. So I get that f prime of x is a negative 3 times the quantity 4x minus 7 on the top over a 2x squared minus 7x plus 5 whole quantity squared on the bottom. But I didn't just want f prime anywhere. I wanted f prime specifically at 3. 3. So f prime of 3, notice I make sure I'm clear about my notation, is a negative 3 times, this will be a 12 minus 7, so that's a 5, right? On the bottom, I get 2 times 9, so I get 18, right? Minus a 21 plus a 5, whole thing squared, right? Seems to me that comes out to be a 2, right? Because I end up with 23 minus 21 essentially, so, 2 squared is what I meant to say. So this comes out to be a 2, and then I'm squaring it, so I get a negative 15 over 4, and that's the answer they want for my slope, and that's it, right? They want the negative 15 over 4. Cool. Part B. Find the x-coordinate of each critical point of f on the interval from 1 to 2.5, open interval. Classify each critical point as the location of a relative min, relative max, or neither. Justify your answer. So it's very likely that this is setting me up to use the second derivative test. Not necessarily. I mean, you know, it's, I take it back, because looking at this is going to be a disgusting second derivative, right? I don't want to do this. So I'm going to do the first derivative test. So let's, over here, off to the side, and you don't necessarily have to be able to see it, but I need to be able to see it because I'm going to have to use it, and I'll just copy it again if you need it. I'm going to write what my f prime is, because on a real paper, I would still have the paper in front of me, but because I'm writing this on a tiny, tiny calendar board for your video, when I erase it, it makes my life a whole lot harder. So, all right, so normally, I would tell you that if you were asked, that the AP is usually setting you up when they ask max, min, or neither to use the second derivative test. But the second derivative test is an awful lot better if you have a nice, easy second derivative, and this second derivative would be disgusting. It would be a quotient rule with some chains, and it's just awful. So let's do the first derivative. So we're asked to find the critical points, right? And they did say from 1 to 2.5 exclusive, right? So here's the kinds of critical points we have, right? There are 3 kinds of critical points. Type number 1, f prime is 0. Well, the numerator of f prime would have to be 0, so negative 3 times a 4x minus 7 would have to be 0, right? Negative 3 equals 0 is a lie, so 4x minus 7 would be 0, which gives me x equals 7/4, and that is smaller than 2.5 because it's smaller than 2, so that's one critical point. The second kind of critical point are where f prime doesn't exist. Well, that's going to mean that the denominator, which is a 2x squared minus 7x plus 5, all squared, but it doesn't really matter because it equals 0. So I'm going to have to factor this guy, right? If he factors. And the question is, does he factor? So if he factors, this is going to be a 2x times an x, and this is going to be a 1 and a 5. But they have to have the same sign, right? So I'm pretty sure I get 2x and x. I can't have the 5 be opposite the 2, right? Because if the 5 were opposite the 2, then I end up with a 10. So if I put a 5 here and a 1 here, and I make them have the same sign of both opposite, negative 2x, negative 5x, yep, that works. And now, really suddenly, it becomes really clear why they gave me the limitations of 1 to 2.5. Because these guys are vertical asymptotes in the original graph. So not only are they the denominator of f prime, but look, they're the denominator of f of x too, so that's why the window is what it is, which also covers the third kind of critical point, which are endpoints, but again, endpoints here that are vertical asymptotes. So the only critical point, my answer is the only critical point is at 7/4, right? So now we're going to look at the sign of f, prime, rather. So here's what I know. I know that I have this window from 1 to 2.5, and I know that the only critical number I have in the middle is 7/4. Well, the numerator of this thing is a negative 12x plus 21, which is a line with a negative slope, right? It's a line with a negative slope. Sorry, there you go. So what that means is if it's 0 here, it's positive before it's 0 and negative after. The denominator is a bunch of stuff that's squared. So the denominator is a perfect square trinomial, or perfect square, well, it is actually a trinomial that is perfectly squared, but that's not what I meant to say, but that's fine. It is a quantity squared, which means that other than the times that it's 0, which created vertical asymptotes, it's always going to be positive. So what that means is that my f prime is positive and switches to negative, which means that what f is doing is going up and then down. So my answers are, the only critical point is that x is 7/4, and it is a max because f prime changes from positive to negative. And again, my gut instinct was, hey, this is probably the second derivative test, but it wasn't a good call to do that, and I realized that about 3 seconds into starting to derive in my head, oh, hey, this is disgusting, and that's okay. That's a thing that's going to happen. All right, part C. Using the identity that, and then they give us the partial fraction decomposition of this, which was super duper nice of them. So this is a partial fractions decomposition problem where they don't make you do the decomposition. How lovely of them. So they do it for you and they just want you to do the calc. No pre-calc required. So, yikes. Time to clean the board. All right, so part C. In part C, we are given that f of x that they gave us breaks down into a 2 over a 2x minus 5 and a minus a 1 over an x minus 1. Cool. They ask us to evaluate the integral from 5 to infinity of f of x dx or show that the integral diverges. So they want us to integrate from 5 to infinity, which is past the asymptotes, right? Because the asymptotes were at 1 and 2.5 of f of x dx. So technically you are not allowed to do limits with infinite bounds, so we cheat and we make it into limits as you approach infinity. So we're going to say the limit as, pick a bound. Did we use a b yet? I don't think we did. So we use b. The limit as b approaches infinity from 5 to b of these two things, right? Now, both of these are pretty straightforward natural logs. If you need u substitution, that's fine. Your u would be the 2x minus 5, so your du would be a 2 dx, which would work out. There's that 2 you want, and your u would be the x minus 1, and your du would just be a dx. So you end up getting that this is the limit as b approaches infinity of a natural log of the absolute value of 2x minus 5 minus the natural log of the absolute value of x minus 1, again, evaluated from 5 to infinity. Sorry, 5 to b, my bad. All right, so if you want to combine these into one, it's not bad. You're subtracting natural logs, so you don't have to, but it does kind of make your life a little easier. If you make this the limit as b approaches infinity of the natural log of the absolute value of 2x minus 5 over x minus 1, using log properties, it's a little bit easier, so from 5 to b. So now I'm going to go ahead and plug in, right? When I plug in, what's going to happen is I'm going to get that this is the limit as b approaches infinity of the natural log of, this is going to be a 2b minus 5 over b minus 1, minus, and then I'm just going to go ahead and plug in the 5s, which is the natural log of, if I plug in a 5, that's 10 minus 5, so 10 minus 5, which is 5, come on, brain, over 4, right, because 5 minus 1. So the question is really, what's this limit doing as you approach infinity? Well, when we approach infinity, this fraction has b's of the same degree, so it's only going to be the leading terms that matter, this 2b and the b, so this thing is approaching a 2. So I'm going to get natural log of 2 minus the natural log of 5/4. And that's not wrong, and that's a totally acceptable answer. If you wanted to combine them together, right, you're dividing by this thing, so that would be the natural log of a 2 divided by 5/4. So the answer the AP has is natural log of 8/5, which is great. Technically, again, this is not a wrong answer, but if the AP wanted to be picky, they have the natural log of 8/5. So it converges, and it specifically converges to the natural log of 8/5. Part D, determine whether the series n equals 5 to infinity of 3 over 2n squared minus 7n plus 5 converges or diverges. State the conditions of the test used for determining the divergence. Okay, so oh my, sorry, need to clean the board. Part D. Okay, so their question is, in part D, basically the same question they just gave you, but instead of using an integral, they want you to talk about a series and whether it converges or diverges. So there are a couple ways to do this. The AP gives a few options. For me personally, I just found, so in part C, I found that the integral from 5 to infinity of this thing, right, I think they called it f of x originally, yep, dx, which is this same, like this is f of n, but it's the same thing. I found that this converges, right? This converges to natural log of 8/5. Like that's its actual value. Like it has, so I don't even have to say converges. I can just say, hey, this is equal to this quantity, right? So the thing is that if, so based on the integral test, right? So f is a positive function, right? So from 5 onward, and you can figure that out by looking at the graph of f, right? So for x values greater than or equal to 5, right? F is positive, right? F is decreasing, right? Which we saw in part B, I think it was B, right? So we saw in B that it was decreasing, in fact, for x values that were after 7/4, right? That we were talking about a decreasing function, right? And it's also continuous because the only places it wasn't continuous were at 1 and 2.5. But again, we're talking for greater than 5. So if f is all of these things and the integral has a finite value, then this thing converges, right? So if all of these things are true, right? So this is true for all these values, and you can see that f is positive for bigger numbers if you want. The easy way to see that f is positive, for the record, is that, so if this is the one that's hanging you up a little, the top is a 3, that's a positive number, and this bottom thing, right, this bottom thing is a quadratic, but we know where its two zeros are. Its two zeros are at 1 and 2.5, so see how it's physically above the x-axis after 2.5. So for x values after 2.5, this thing is positive. It is decreasing for f values after, or for x values after 7/4, and it is continuous for everything except 2.5 and 1. Based on all those qualities, if the integral converges, then so does the function, or so does the series. My bad. So the integral test is one way to do it. The other way to do it is, slightly more abstract. I can't imagine that you wouldn't go to the integral test first, given that you just integrated this in part C. Had I not had to integrate this in part C, I might not have gone to the integral test, right? But since I already had to do this in part C, it made the most sense to just lean on the work I had already done in C and show that by the interval, show that this converges by the integral test. So the other option is to use limit comparison, right? You can't use direct comparison, but if you want to use limit comparison, right? To use limit comparison, you don't need to show that this quantity is strictly smaller or bigger than anything. You just need to pick something that behaves kind of like this, right? So my argument is that this thing behaves like a 1 over n squared, which is a really simple p series, right? I'm going to argue that this thing behaves like a 1 over n squared, right? So the limit comparison test says that if you do the limit as n approaches infinity of the series you want to know about, divided by the series that you know the behavior of, and you do know that 1 over n squares converges because it's a p series. If you do this limit over the value that you know behaves a certain way, and if you clean this up, you're going to get a 3n squared over 2n squared minus 7n plus 5. And it's the limit as n approaches infinity. And because these degrees are the same, it's the fraction of the leading coefficients, so this thing is a 3/2. If you do this limit comparison test and you get a finite value, right? Since I got a finite value, what this tells me, finite non-zero, I should clarify. Finite non-zero value, what this tells me is by the limit comparison test, they behave the same. So this one behaves the same as this one, right? So what I mean by that is if 1 over n squared converges, so does 3 over 2n squared minus 7n plus 5, right? So again, if I probably would have been more likely to do the limit comparison test than the integral test if I had not been asked to do part C before this. The reason I went to the integral test first, which is not usually my gut instinct on a problem like this, is because you were specifically asked to integrate it in part C, and so then you could use your work from part C to answer. So there you have it.